Welcome guys, day 3 of the online notes, and tonight's chapter is on acceleration. This is kind of a word that you guys have used before, and I can almost guarantee you used it incorrectly in certain cases. You guys always think acceleration means speeding up, but I hope to show you tonight that it's not always meaning speeding up. So let's get started. Quick review from stuff we talked about last week. You know speeds measure distance over time. Velocity is a vector. Remember the cartoon? That was awesome. Remember, vector is a magnitude with direction, because we're going to use that tonight because acceleration actually plays an important role with that. So acceleration by definition is the rate of change of velocity. So if you read that carefully, rate of change of velocity, and essentially acceleration is any change in velocity. You can think about ways we can change velocity. We can, right here, we can change the speed. Okay, that means speeding up or slowing down. This is kind of the biggest thing kids always confuse themselves with. They think that acceleration must mean speeding up, but it doesn't have to be speeding up. Technically, if you're slowing down, you are still changing your velocity. So, if you also think about velocity, remember velocity is a vector, so it's magnitude with a direction. So we could say north there. Well, if I change my direction, all of a sudden I'm heading in this direction. Didn't I technically change my velocity? So, hence, a change in direction is also acceleration. We look at 3 ways to cause acceleration, like I was just saying. If you look at all of these over here, you got your green light right here. If you're speeding up or a change in speed, car speeds up at a green light, clearly that's a change in velocity. That's going to be acceleration. Now, alternatively, or quite the opposite of that, let's say a car all of a sudden comes to a red light, it's going to have to slow down. For those of you who don't have your license yet, that's what a red light means. You come to a stop. So, come to a stop, you've got to slow down. So that, once again, is an acceleration. Just slightly different. You can think of it, it wouldn't be a positive acceleration, it would be a negative acceleration, which we'll talk about in just a little bit. And the last way, let's just say you're simply taking a turn here. You can also take a turn, and that technically, once again, changing your velocity, and a change in velocity over time is acceleration. Zero acceleration. So, acceleration to be zero, we can think of this a couple of different ways. You're traveling at a constant speed. In other words, if your speed isn't changing, you have no acceleration whatsoever. If you're traveling at a constant speed in a circle, would your acceleration be zero? And the answer is what, guys? Think about it for a second. Keep thinking. If you thought long enough. You ready for the answer? Alright, here it comes. You are still technically accelerating because you are constantly changing your direction at that point in time. So, as we're traveling around the circle, we're changing our direction. Therefore, we are still accelerating. I know we're not changing our speed, but we're changing our velocity, which by definition is a change in acceleration. Let's get to the math part, everybody's favorite part of this. The equation for acceleration is VF minus VI all over T. Now you've seen V's and T's before, but you haven't seen VF and VI just yet. And it's really no different than what you've seen before, but VF stands for final velocity. Yes, that is really literally the worst way I could ever have written that. And this is initial velocity. So it's the final velocity minus the initial velocity all over the time it took for that to occur. If you look at the units, you'll see something very particular here. The units for acceleration are meters per second squared. And I'm going to talk about that in just a little bit, specifically what that means. Here's the triangle. I know it looks a little different, and kind of the big thing here is all of a sudden we have 2 variables up top. We have both the final velocity and the initial velocity here. But it's important you remember that VF minus VI over A and T for the triangle. One key thing, and I'll show you kind of how to derive this tomorrow, is that if you're solving for final velocity equals acceleration multiplied by the time plus the initial velocity. Sorry about that, that got cut off there. Solving for time, once again, you can look at it up here. If we cover up this T, we have VF minus VI over acceleration. Just kind of using the triangle, just looks a little different now because we have two variables up top. But really the rules still stay the same. Numbers never lie, of course. So small acceleration means velocity is increasing gradually. And on the opposite end of that scale, if we have a large acceleration, our velocity is changing very rapidly. Positive acceleration means we're speeding up. Negative acceleration means an object's speeding or slowing down, excuse me. So if you think about the positive acceleration, that was the green light example I gave you, speeding up. Negative acceleration would be slowing down, or what you guys commonly call deceleration. But please keep in mind, guys, that deceleration is still an example of acceleration. It's just a more specific type, acceleration in the negative. So let's do a couple examples, and then here are these examples. I'm going to begin to talk about what this actually all means. So why don't you pause it right now? I want you to take the time to pause it and actually try this equation, and then we'll give you a second. And Alright, you should have done it, so here we go. The example problem says you are driving from school home and your speed goes from 10 meters per second to 40 meters per second in 5 seconds. So you guys know the first thing we always do is write out what was given to us in the problem. So speed goes from 10 meters per second to 40 meters per second. We have an initial velocity there, which was 10 meters per second. We have a final velocity, which was 40 meters per second. And we have a time, which was 5 seconds. Now, if you recall earlier, I gave you the equation for acceleration. It's a equals vf minus vi over t. At this point, we are very simply plugging in the plugging in the variables. My VF was 40 meters per second minus 10 meters per second. All of this was given to us over my time, which was 5 seconds. 40 minus 10 is 30 meters per second divided by 5. I'm running out of my screen here, and I'm pretty sure you can see 6 meters per second squared. This squared is super important. So let's talk about what that actually means. Meters per second squared can also be written meters per second. And I know that sounds a little confusing, but if you think about it, what we're telling you is that as you were driving home from school, your speed increased by 6 meters per second every single second. And you can check yourself, because how long did we take? We took 5 seconds, and if every 5 seconds we increased by 6 meters per second, that's a total of 30. And that makes sense because we went from 10 meters per second to 40 meters per second. So keep in mind, just like the gas laws had a logical approach to these, how you could check your answers, so do the acceleration problems. You just kind of remember the meters per second, which I know sounds a little confusing. We'll talk more about it. Another example, guys, I'm going to let you try this one on your own, and then we'll come back to this one in class. So why don't you pause this one now, try it, and then we'll check your answers tomorrow in class. Let's talk about gravity, because gravity plays a really large role when we talk about acceleration. All of a sudden we see that gravity actually is a type of acceleration. And we're going to write it out here. 9.8 meters per second squared. In other words, anything that you drop in a vacuum. No, not a vacuum cleaner, smart people. Vacuum is an area with no air in it. That means there is no air resistance. And really on this earth to find a perfect vacuum is next to impossible unless we create one. You can remember that YouTube video I showed you with the marshmallows. That was a vacuum that had no air in it. But saying in a vacuum that if you drop something, it would fall at 9.8 meters per second squared. In other words, every second you let something fall, it would fall about 10 meters per second. So if you think about that, if we let something fall for 3 seconds, how far down? What would the final velocity be? 30 meters per second. Because for every second we let it fall, it increased the speed by about 10 meters per second. We'll talk a little bit more about this tomorrow. We'll do a couple demos with this. Law of universal gravitation. So this is where we'll really get into theory tomorrow, and technically what we're saying is that everything on this earth has some sort of gravitational pull. believe it or not, that the computer sitting in front of you does have a gravitational pull on you. But the reason we don't really see objects floating towards us in these cases is because we have one object here that's a little bit bigger than all of us. That, of course, is the Earth, the thing we're actually sitting on. No big deal. And we'll talk about why no one else sees that. But gravitational force between two objects depends on only two things. It depends on the mass of those two objects, and it depends on the distance between the two objects. As mass increases, or as mass goes up, the gravitational force goes up. So that's a direct relationship. But as distance increases, our gravitational force decreases. So much like the gas laws, again, that's an inverse relationship between the two. So just think, more mass, more gravitational force; more distance, less gravitational force. We'll talk about some real-world applications for that tomorrow. Universal gravitational math. I'm going to tell you right now, guys, write this equation down. Alright? It is a force here. We have gravity, mass 1, mass 2, and the radius squared. We'll talk about this all in class tomorrow, I promise. I know it looks incredibly complicated. No, I'm not going to ask you to solve many of these. It'll be fine. We'll walk you through them. Here's the More Math Continued. Please, please, please take a look at it. Come prepared, ready to roll tomorrow, and have those notes filled out. If you have any questions, write them down on the left side right now while you're going through this. That way you can ask them when we get in. And be prepared for your 5-question quiz. See you tomorrow, guys.